Good afternoon, everyone. First of all, thank you for joining the session. I welcome you all to the second day of our hands-on training program. We are thrilled to see you all again, ready to dive deeper into the practical aspect of the tool and concept introduced yesterday. Basic Day 1 laid the foundation, and today we will build upon that with more in-depth session, guided exercise, and real-world application. Our team is here to support you every step on the way. So don't hesitate to engage actively and make the most of the experience. In today's session, basically we learn about the relaxation process and DFPT based property calculation, density functional perturbation theory used in phonon dielectric constant and forces, and structure relaxation workflow, convergence criteria, energy and force minimization. Relax a silicon structure, analyze forces, energy, convergence, and final geometry. Run a DFPT simulation and interpret result. I hope everyone installed the device studio software. If someone facing any issue, let me go through the installation process first. Everyone received a mail like this. Go to the drive and download. Click on download anyway. Click on download section and save. After downloaded, you can see our zip file device studio 2024 Windows. Right click, extract all, and according to your location, you can browse. I do in D drive because in C drive I have not enough space. Select folder and extract all. Here you can see device studio Windows. In bin folder, download the license file also. Here you can see, copy the license and in bin folder, paste the license here. You can see here at jwtech.lic. At the above section, you can see device studio.exe application file. Double click to open it. Here you can see it's open the GUI. At first, you can see create a new project, open an existing project. Let's create a new project. Click on OK and give some name. And click on save. Here you can see in project, you can see hands-on training day 2. I save this project with this name. First, you can see here the project folder where you can import material. All can be seen here. And at the below section, you can see the properties. It shows the basic properties of all atoms and elements. And at the below section, you can see the job manager where SCF input your parameters will be run. and it will show the condition status like running in queue condition and their process also. At the top, you can see menu bar, and at the below section, it is a toolbar option to create your crystal and atom and device. At the left corner, you can see file option. Click on the file. You can see new project. You can click on new project by creating a new project. At the file option, you can open your existing project also and save project. At the below section, you can see new device, crystal, and molecule for creation. If you want to import your material, here you can see import local and import online. Let's import local. Our software provides a lot of material. You can see here organic material, 3D material, 2D material, 1D material, and 0D material. Let's go in the 3D material and layer material and click on the MOS2. Here you can see our software support multiple material format like HJW, XYZ, CIF, OSCAR, SCF input, relaxation, and molecule PDB. Click on Open. Here you can see our material file has been imported. I hope everyone import their material. Please confirm. Again, I repeat, same thing. Go to the file, import, import local. Then in 3D material, go for the layer material. Here you can see MOS2. Click on this, then open. I hope everyone import their material. Here you can see total number of atom here 9 and their formula MO3S6 and total area of lattice and their XYZ coordinates. Left click of the mouse and click a drag option here. You can see left click of the mouse and drag a box. It selected 2 atoms and go on the delete atom. I again repeat, left click of the mouse and drag a box. Basically, select the atom and click on the delete atom. After that, you can see here also atom. Left click of the mouse and drag a box. It will select it. Go to the delete atom. Left click of the mouse and select and delete. Again, select this atom. And here you can see center. Click on the center. I hope everyone completed here up to here. Again, I repeat the same process, whole process. I undo all the process. Here you can see left click of the mouse and drag a box. And here you can see delete atom. Click on delete atom. Again, drag a box and select these atoms and click on delete atom. Again, drag a box. Here you can see center option. Click on center option. I hope everyone is completed up to here. Again, go to the simulator option. In simulator, you can see nano detail, nano scheme, and rescue. Nano detail for the device and material simulation. Nano scheme for the tight binding. Rescue for material simulation with hybrid exchange correlation. In rescue, you can see SCF calculation. Click on the SCF calculation. Here you can see it pop up a new window. You can see a basic setting like smearing sigma, resolution, method, exchange correlation, key point sampling. In method, you can see real space and LCO, linear combination atomic orbital. In the same way, in exchange correlation, multiple exchange correlation are given like local density approximation, GGA, meta GGA, hybrid. That's by default for the LDA. And in the iteration control, you can see charge density, total energy, and maximum SCF iteration step. You can increase also. Let's go for the default value. You can see mix method also, Pole, linear, down, and mix variable also, density matrix, and potential. If you go to the basic set, here you can see LDA plus U. It's basically Hubbard. Basically, here you can see S, P, T, and F. You can enter your value also. It basically uses when you choose the transition elements. Let's undo this. You can see double zeta polarized atomic data and user defined also here. Let's go for the double zeta polarized in this here. And in spin, you can see spin type, no spin, collinear spin, and general spin. If you click on the collinear spin, you can see magnetic movements you can apply, and you can change the value also. In the general spin, you can also include spin orbit interaction. Let's go for the no spin this time. Again, I repeat the same process. Go to the simulator, rescue, SCF calculation, and by default, parameters are given. If you want to change, you can change according to your need. Iteration control, basic sets, and spin type. At the below section, you can see generate file. Click on generate files. In the project section, you can see it created a folder MOS2. In MOS2, rescue crystal and SCF input file has been generated and atom.xyz. If you click and right click of the mouse, it's open the toolbox like run, open with, and open containing folder. Click on open with. Here you can see the script of the SCF input file which created through the GUI like info calculation type, eigensolver, LCO status, and K point sigma. You can also see mixing type, density, mixing method, and elements, and their pseudo potential like zeta polarized. You can also edit the script also here. If you want to change something, you can change and click on the save option. Here you can see atom.xyz. Open with. It basically tell about the Cartesian coordinate of the crystal like MOS2. Here you can see SCF input. Right click. Here you can see run option. Click on run and click on run. It basically open the job status. Close this window. At the job manager, you can see SCF input file in running condition. Again, I repeat the same process. Click on SCF input, right click and run option and run the input file. And it will show in the job manager. You can see here in running condition. And you can see also the process here. For the time being, again, go to the simulator, rescue, and go for the analysis to find some parameters. Here you can see here, density of state, band structure, potential. Let's find the band structure and density of state. By double click, you can directly come here. Click on the band structure. You can also click here. Double click on density of state. It will pop up here. Click on the band structure to enter their parameters like symmetry K points. Go to the path. You can see below zone path and their point GMKG. If you want to delete, you can also click on this and delete. And you can also add new. You can see delete, delete. Go to the preview and apply. Clicking on the path, you can open this below zone path. You can see the number of K points and empty band and partial weight band calculate. In the same way, click on density of state. Here you can see K point sampling. Let's increase to 3 up to 2. Let's go for the 2. And energy range -10 to 10. And number of energy point, K point sampling. In K point sampling, you can see Fermi direct, Gauss, tetrahedron, and multiple are given. And sigma are given 0.01 electron volt. You can see generate file option are given. Click on this. It will generate band structure dot input file and density of state input file. Again, I repeat the same process. Go to the simulator, press Q. Here you can see analysis. Click on analysis. You can see band structure. By double click, it will pop up here. And density of state also. Click on double click. You can see here. Click on band structure to change some data. In the same way for the density of state. And click on generate files. Let's click on band structure dot input file. Right click. Open with. Here you can see the script of band structure dot input files. K point gate and symmetry GM KG and K point sim points, icon solver, empty bands. You can also edit and save. Cancel this. In the same way, density of state input file here, script, it created the script through GUI. You can see info calculation type, LCO status, and K point sigma and K point grid. And you can also change like DOS range to the script also. Like if I change to 5 to 5, here you can see you can also change to the script also and click on the save option. Click on the band structure.input file, right click and click on run. You can see SCF input file has been completed at the website. Close this window. Again, click on desktop state input and click on run. Here you can see in the job manager, band structure.input file in running condition and density of state input file in true condition. To see the process, click on this. It will take some time, then it will start. You can see it started. For the time being, let me go through the text toolbar. Here you can see at the last option, here distance. Click on the distance. If you click on the one atom and control, click on other atom. It basically tell about the distance. I repeat, click on one atom, then control and click on second atom, and it will tell about the distance. Here you can see the angle option also. You can see it tell about the angle.
Uh, Sorry, but I didn't get that distance or angle.
Yes, ma'am. Click on this distance option, then click on one atom and control. In keyboard, control option is given CTRL, control and left click of the mouse on the other atom.
Okay, okay, thank you.
In the same way, for the angle, click on the angle and click on this control. It will tell about the angle. You can see it started the band structure calculation. For the time being, let's create a new project also. Click on File and click on the New. And here you can see Crystal. Click on Crystal. I hope everyone is open the Crystal Builder. Go to the File, New, then Crystal. Here you can see the Brevis lattice and space group. Multiple space group are given here. Yes, ma'am. Multiple space group are given. You can choose according to your data. And here you can see A, B, C, alpha, beta, gamma. Let's take default value and go for the plus icon. Here you can see P1, P2, and P3 are in the fractional coordinates. Click on 0, 0. Here you can see plus icon. Click on this. By default, it will take carbon atom. By double click on the carbon, you can see it will open the periodic table. Let's go for the silicon and OK. I repeat the same process. Click on plus button. By default, carbon element is selected. Double click on the carbon element. It will open the periodic table. Click on silicon and OK. Again, click on the plus button. Go for the 0, 0 and enter the fractional coordinate like 0.25 for P1, 0.25 for P2, and 0.25 for the P3. I hope everyone enter their data. Go for the primitive cell and click on preview. Here you can see it created the structure. You can also see the symmetry operation here. Click on build. Here you can see it created the crystal.hjw W material file. Again, I repeat, go to the file option, then new, then crystal, and enter the element by plus. You can change by clicking on the carbon atom and choose silicon and click on plus at plus button and enter the fractional coordinate like 0.25 and first click on the anywhere here and click on the preview. Then it will show. And click on the build option. We already done this. You can see the structure is not optimized. Then go for the simulator. In rescue, you can see the relax option are given. Click on the relax. It will open the new window like relax calculation for crystal. You can see basic setting like resolution, real space, LCO, LDA, exchange correlation, and K point sampling. Here you can see relax option is also given here. Their method like cosine Newton, steepest, conjugate gradient. Go for the cosine Newton this time. And iteration control like charge density, total energy, number of steps, mix method, and mix variable. In the same way, basis set and spin type. Click on generate files. Here you can see it created a folder crystal, then rescue crystal, relax.input, atom.xyz. I repeat whole process again. Go to the simulator, rescue, then relax. And if you want to change some data, you can change and go for the relax iteration, basic set, and spin type, and click on generate files. Here you can see it created a relax.input file and atom.xyz. You click on the relax.input file, right click. Here you can see run, open with, and open container folder. Click on open with. The script of relax.input file, here you can see. Info calculation type where result has been stored, icon solver, LCO status, and their subparameters like cosine Newton method. Here you can see here structure relaxation method, cosine Newton, and to their tolerance and atom.xyz. Right click, open with, and their Cartesian coordinate points. Right click on the relax.input file and click on run. In the job manager, you can see our relax.input file in queue condition. And for the MOS2, band structure.input file has been completed here. You can see. Here you can see it create a log file also, rescue log.out file. Right click, open with. It basically tells about the total times, methods. Basically the log file for the running condition. If you right click, you can see open containing folder. If you click on any input file like sf.input, right click, here you can see open containing folder. Click on open containing folder. It will show the path of your project. You can see at the top, result folder has been created. Go to the result. You can see here band structure, density of state has been given. Again, go to the device studio. To see the result of the band structure of MOS2, go to the simulator, press Q. At the bottom, you can see analysis plot and open your project path. Like go to the documents in the device studio project. You can see here device studio project, and our folder name has been hands-on training day 2. You can see here hands-on training day 2. Click on this. You can see there are two folders, MOS2 and Crystal. Click on MOS2, rescue Crystal, results. Click on the band structure.txt file and open. It will show the band structure diagram. I hope everyone get their result. Someone facing an issue, please ask. And you can also export this image in the text file also, and you can save export image. You can see here export image in multiple image format. If you click on the no spin option, you can also see the number of band. And for the same, for the density of state.input file, go to the simulator, rescue, and analysis plot. And here you can see density of state and density.txt file. Let's go for the density. You can see 3D view, draw model like 3D, 2D, average along Y, and average along Z direction. In the same way for the 1D also. Average in XY plane, YZ plane, and XZ plane. You can also export in the multiple image format. You can see image and text format also. For the density of state, go to the simulator again, rescue, analysis plot, and the path of your folder. You can see here density of state and open. You can see density of state for the MOS2. I hope everyone get a result. You can see the left.input are in running condition. At the right corner of the below side, you can see here setting. You can see machine option. If you have high-end system, you can also connect with new and enter their details like computer name, host IP, username, password, their working directory, and you have a cluster. Go for the PBS and slum files and click on OK. Let's go for the file option here and go to the import. You can see here import local and import online. You can also import your material online. Click on import online. It will connect it to the material project API. Let's go for the aluminum nitride, ALN, and click on the search option. Quickly go to the file, import, and import online. You can see it will pop up with different space group like F43M and their properties also here. Let's go for the P63 TMC. You can see also their data also here and click on add option. You can see it imported successfully. I repeat, file, import, import online, and write any material file and click on search option. You can see here aluminum nitride. Left click of the mouse and drag a box and click on center. Left click of the mouse and click on center. You can again go to the simulator. In this project, we will go through basically for the Raman property, optical property like this. Go to the rescue. In rescue, you can see we go through the SCF calculation and relax. Now it's time for the DFPT, density functional perturbation theory. Click on the DFPT calculation for the crystal. You can see here, it will pop up the new window. In basic setting, you can see here task. In task, you can see phonon band structure calculation, phonon density of state calculation, phonon band structure and phonon density of state calculation, optical property calculation, and Raman property calculation. Click on the optical property calculation. You can see and their sigma value and resolution and a HCF method like real space and exchange correlation and K point sampling. Iteration like charge density and total energy tolerance value, SCF steps, mixed method, variable, and eigenmatrix iteration. And in DFPT parameter, you can see here DFPT method, Steinheimer, and CFSI. Go for the Steinheimer. And in the basic set, you can see here ammonium and nitrogen. You can see here by default, it will select a double zeta polarized. If you want to change, you can also go for the user defined. In the spin type, go for the no spin this time. And in optic, you can see damping factor and electric field directions. Click on the generate file. You can see here, it will create the folder rescue DFPT where scf.input file has been created, dielectric.input, phonon.input, and optical.input. I repeat the same process. Go to the simulator, rescue, then DFPT, and enter some parameters and go for the default value. If you want to change, you can change. And here in the task, go for the optical property calculation and click on the generate file. You can see here scf.input file, their script, It also created a dielectric.input file script where the FPT matter will be Steinheimer and their tolerance value, and phonon.input file and their scripts, and optical.input file and their scripts. Right click and click on run option. Again, for the dielectric.input, right click, run. For the phonon input also, right click and run. For the optical.input, right click and run. In the job manager, you can see here our relax.input file has been completed. And for the aluminum and nitride, SCF input will be running condition, then dielectric.input in Q condition, phonon.input in Q condition, and optical.input in Q condition. Let's see the result of relax input file. You can see here it created a rescue log file. Open with, you can see it's computing non-local forces sum. Right click, you can see here open containing folder. Click on open containing folder. Here you can see the previous one, atom.xyz and relax structure.xyz new material file has been created. You can see here relax structure.xyz. Go to the file to import the relax structure xyz file. Import local and go to the project in documents where project has been stored. Device studio project, hands-on training, day 2, and for the crystal, you can see the name with the crystal. You can see a relax structure.xyz file. Import is open. It basically relax optimized structure of the silicon. If you measure the distance, like let's measure the distance, click on this and control. You can see here 2.064 and the relax structure. Click this and control. You can see it changed the bond length. Basically, it optimized the structure. It changed in the bond length 2.479, and before the relaxation 2.064. To import the relax structure.xyz material, you have to go to the file option, import local, and go to the project where project has been stored. File, import local, and go to the documents, device stored the project, and hands-on training day 2 in the crystal, rescue crystal. You can see here relax structure XYZ. By clicking open it, it will show the relax structure here, and you can compare their bond length by clicking on the distance option. You can see our DFPT SCF.input file has been completed, and dielectric.input has been completed, and phonon.input in running condition. If you move to the top MOS2, you can see here MOS2. And if you want to create a supercell, go to the build, and here you can see multiple tools are given. Click on the redefine crystal, and you can engage for the face center also, and click on the build option. And if you want to create supercell in C direction, again go to the build, redefine crystal, and increase the length in C direction, like 12. You can see here. If you want to create supercell, then go for the redefine crystal. And for the graphene, you can move to the graphene nano ribbon. And for the armchair, you can create like 4, cos, 0, and preview. And you can also passivate with hydrogen by clicking on this and preview. It will create the graphene armchair, and click on build if you want to create graphene nano ribbon. And if you for creating arm zigzag graphene, go for the 2x2 and preview. You can see it is a zigzag graphene, and click on the build if you want to create zigzag graphene. And for the graphene nano also, you can also change by clicking on this and select any atom and increase the crawl vector. It will create nanotube structure. And click on the build option if you want to nanotube. Go for the graphene nanotube. For the time being, let me show the also the documentation for the rescue software. Go to the Chrome and type Nano Academy. Here you can see Nano Academy technology. Click on this. Go to the below section of the website. Here you can see access the documentation and tutorials. Click on documentation and tutorials. Here you can see the product of Nano Academy, Nanotical, Nanotical Plus, Rescue, Rescue Plus, QTCAT. Go for the rescue. And you can see all the steps like introduction, installation, getting started, and the tutorials. You can see there are multiple tutorials given, like graphene PDOS. You can also visit this website for the documentation. You can see our output has been completed, input file has been completed, phonon.input has been completed, optical.input also completed. To see the result, click on sf.input, right click and go to the open containing folder. Again repeat SCF input, click on SCF input, right click, open containing folder. You can see here at the top side, result folder has been created. Click on this. You can see here aluminum nitride dielectric H5 material file also. It will open in MATLAB. You can see like density, potential. To plot density and potential, you can move to the simulator, rescue, analysis plot, and go to the project path first, document, device story project, hands-on training, day 2, and here you can see aluminum nitride. Go for the rescue TF50 result, and you can see density. It only supported text format for time being, and open. It opens the density 2D view along X, Y, and Z, and 1D in XY plane, YZ plane, and XZ plane. To plot the optical properties, optical input file, click on the optical.input file, right click, and open with. You can see here optical.input, right click, open with, and write a single line script like rescue plot, and copy the ever path, control C, control V, and dot mat file. I hope everyone has written this script, this line, rescue, and P, dash P, and after that, path up the this one, second line, and dot mat to plot the diagram. Click on save option and cancel this, and click on optical dot input, right click, and again run the script. You can see here in any condition, it will show some graph for the optical dot input file. For the time being, let's open the MATLAB. You can open MATLAB online also. You can see here MATLAB online. You can see here by creating an account, you can also go for the Open MATLAB online. Click on Open MATLAB online. If you have already software in your system, you can see here. You can go to the browser project here. can see here. Click on this. You can see here. Select a new folder. Go to the document, device studio project, and hands-on training day 2, and select folder. Go for the layer 2 and 2. Then the studio PT. In result, you can see here. Also mat file. You can see also here data also. It will take some time. You can see also the data here, like elements, X, Y, Z values, and their matrix. You can see also data. And let's create a new project. Go to the build option, then molecule 2D. Here you can see draw cyclohexyl. Click on this and drag it. Again, go to the single bond here, draw single, and click on the corner and draw for all. Again, I repeat the same process. Go for the cyclohexyl, drag, and go for the draw single. At the top, you can see a C option. Click on C to choose the element and click on H and replace with C. Click on the C to replace with hydrogen. And click on apply data. You can also see the properties here and click on apply data. You can see here it created a molecule.hjw. You can also see a chemical formula C6S6 and total number of atoms. At the top toolbar, you can see a force option is here to minimize the structure, basically optimize the structure. If you click on this, you can see multiple force field are given, like universal force field, GFF, chemical, MMF94 and 94S. Go for the GFF. It basically minimize the structure. Take some time. You can see it optimize the structure. It basically change the bond length also to minimize the structure. Basically relax the structure. Go for the simulator, rescue. First, drag a box, and you can see first we have to convert to crystal first. You can see here, convert to crystal. Change the value, like go for the 2020 and 50. Again, go to simulator, rescue. You can see it will enable. Click on TFPT, density functional perturbation theory. Open it. In basic setting, let's go for the Raman property calculation. You can see here. And SCF method like real space and exchange correlation. Also, increase the sigma value and iteration control. Go for the default value. Here you can see charge density, total energy, SCF method, mix method, variable, and history. And DFPT method, Steinheimer, and CFSI. And basic set, you can see atomic data given. Go for the double zeta polarized. Spin type and their Raman properties like damping factor, income photon polarization, outcome photon polarization, and their temperature. And click on generate file. You can see it created the input file here. SCF.input, dielectric, phonon, Raman. Again, I repeat process. Go to the simulator, rescue, TFPT, and some basic setting like Raman code for the task, Raman property calculation, and Simulink sigma, and resolution and exchange correlation and spin type like no spin, general spin, collinear spin, and some Raman property like damping factors, income photon polarization, outcome photon polarization, and temperature. And click on generate file. You can see it created scf.input file and open with. You can see here the value. You can also change like semi sigma will be 0, and you can save this and the script of the scf.input file for the dielectric.input also and phonon.input. You can see the script and for the Raman. Right click, run this script. For the dielectric.input also click on run, and for the phonon.input also click on the run button and run the input file, and for the Raman.input file also. You can see our molecule input file has been run in condition, then dielectric.input in Q condition, and phonon.input also in Q condition, and Raman.input in Q condition. For any project, if you will find to optical, Raman properties, phonon density of states, go for the rescue, TFPT, and in basic setting, you can see here task. You can find any properties and click generate file, and you can run all the input file, it will generate. I'll show the some of the previous result. You can see for the aluminum nitride, I find the Raman properties, Raman and optical also, both. You can see here dielectric permittivity and energy for the aluminum nitride. And intensities, IR intensity, you can see here, you got it. Energy loss and refractive index. You can see here refractive index. And Raman shift, Raman intensity, polarized here you can see here. For the average Q1 also, Raman shift. You can see scf.input file in running condition. Again, go to the file, then import and import online. go for the boron nitride and click on search. You can see here with different space group, all material will be given. Let's go for the B4 and 4 with space group PNMA and click on the add button. You can see it imported the material file. Go to the file, import and import online. Import, import online and click on boron, add right and search. And with different dispose group are given here. You can select first one and add, and it will show this like. Again, go to the simulator, rescue, TFPT, and go for the Raman property calculation. And all values will be same. 0, rotation control, basic set, and go for the double zeta polarized. You can also user define. Some of the pseudo potential are given in our project, like device studio. You can see here rescue atom database, general. You can see atomic data and double zeta. Go for the atomic data and open. Same for the nitrogen. Go to the device studio. At the bin folder, you can see at the bin folder below section, you can see rescue atom database, general, and go for the nitrogen. You can see here atomic data and double zeta polarized material file are given. Click on this and open. You can see also spin type and Raman properties. Click on generate files. You can see the script also. Right click and run all the input files. You can see all in the running condition and some queue condition. You can also move the atom by selecting this left click of the mouse and select. Here you can see at the toolbar section, move option are given. You can see translation along XYZ, unit cell vector, and screen view. Go for the screen view, and you can also assign distance also, like 0.2 angstrom, like it's moving the that direction. The same way, you can do this. By selecting this atom, click on the move atom and translation along screen view. You can assign the distance also, and by moving right up and down, you can move your atom direction. In the same way, if you left click of the mouse and drag and select call atom, you can see here mirror atom. can see go for the XY and apply. You can see it create the mirror structure. Again, I repeat, left click of the mouse, select all atom. Here you can see mirror atom are given. Click on this, go for the XY plane, and you can also assign the distance like 2 angstrom and click on the copy option also and apply. You can see here it create a mirror structure of same molecule. Left click of the mouse and drag and select all and delete this. Again, left click of the mouse and select all atom. Here you can see rotate atom. You can also rotate your atom according to given the angle. You can also change like 90 degree and you can change same way. It's basically for the tap along A direction and B and C. If you want to replace any atom with other atom, click on any atom and here you can see replace atom option. Click on and nitrogen and you can replace. You can see here it replace with nitrogen. If you want to add atom in between them, click on here and click on any atom like oxygen and put the mouse here. It will add this atom at its place. You can see at the property section also oxygen and XYZ coordinates. Select all. Here you can see last option, recalculate linker bond. It basically create the bond with the oxygen. You can see. Input file are in condition, in running condition. It will take some time. For a time being, if anyone have doubt, please ask. Anyone have doubt, please ask. You can see here in the MATLAB. In the MATLAB, you can see here. Go for the browse for folder. You can see option here, browse for folder. Open your project here, like in documents. You can see a device studio project and go for the my project name will be hands-on training day 2. Click on this and open anyone and select folder. You can see here like their material file, basic set material file, aluminum and the double zeta polarized material file. In the rescue DFPT, you can see the result also. Basically, MATLAB is used for the visualization and get some extracted data like XYZ and material files. And for the device simulation, you can find also IV curve conductance here. For the device, for tomorrow, we can create the device using our nanodecade software, where we can create transistor and silicon PN junctions and find some their properties like photocurrent, thermoelectric constant, effective potentials. And you can create your molecule using molecule 2D and molecule 3D also. You can see here, build molecule. You can see it will open molecule 3D structure. You can see here plus button. Click on plus button. It basically add atom. You can add like carbon and go for the tetrahedral shape. And you can see here by clicking on this, it will automatically come here. And if you click on the another atom, wait, you can see it add multiple. And you can also click on add nitrogen, go for the single atom, and you can change like this. And if you want to add hydrogen, you can see add hydrogen option. Click on this. You can create complex structure here also. At the last section, you can see here. Basically, biofragment material also given here. You can see here. A lot of material given. You can use for the biosensors and other things. And click on apply data. You can see. And for optimization, go to the force and go for the universal force field. You can see it basically optimize the structure. And in the same way, for molecule 2D, you can create complex material using different fragments. You can see here. You can add the plate. With hydrogen and add complex material also here. You can create and apply data. Anyone else? Wait for 1 minute. Anyone else who are facing any issue regarding the installation or creation of device or crystal structure? I'll show some of the previous project which I created earlier. Go to the file, open project. You can see I created multiple project here. Open this project, rescue test. You can see for the aluminum nitride, I find the properties like Raman property and non-band structure also. And for this crystal also. Fine. Open project. You can see here the zinc oxide basically I take from the import local from 3D material uh, from metal oxide. I basically imported the zinc oxide. You can see ZNO and redefine. Here you can see with different atom. I basically replace with other atom. You can see here copper and find some band structure. You can see here. And for the doping and undoping, you can see it will show that some difference in band structure also, undope and doping. Anyone have query? You can also follow the documentation by provided by Nano Academy to get more insight and get more tutorials about rescue software and nanotical software. And you can see also here, if I connect to the other system, and someone asking for the biomolecules, go to the build in molecule. You can see here. You can drag, and according to it, you can change also the atom and the structures and click on apply data and find their properties also using our rescue software. You can see here, talk to Mike basically. Again, mm, molecule, you can see n number of biomolecules are present. like central residue and cytosine and climatic acid. You can see. You can directly import here and click on apply data. If we want to create a graphene in 2D material, you can see graphene material file, open, you can see, go to the build and redefine crystal and go for the 10. You can see here. You can also change in the B direction also. And create graphene, 2D graphene, bi-layer structure also. If you want to export coordinate also, you can see here, display style, display atoms. If you click on the display atoms, you can see the XYZ coordinates. And you can also export this. It will save in C user tel documents and in hands-on training graphene dot value format. It will store the XYZ Cartesian coordinate points. If you right click on the screen, you can see a labeling option. You can see a label, object type atom, and number of atoms. Apply. You can see number 1, number 2, number of atoms. You can also remove by clicking on this. If you want to change background setting, you can also change here. And in display type, you can see line option and ball and stick option for to show the atom and all elements. In the same way, you can create the lattice and you can see it is created in a range. You can see the C dice. You can see here. Anyone have doubt? Please ask. From tomorrow, we basically go for the nanoticle, where we can simulate an silicon PN junction, device simulation, and find some parameter like JT, effective potential, IV curve, transistor, conductance. And from tomorrow, my colleague will guide you for the nanoticle software, Sahil Verma. Okay, thank you for the today's session. See you tomorrow.